Now let's take a look at how we can learn the visual appearance of a three-dimensional object. So let's say that you were given this object right here, and I said to you, memorize this object so that you can recognize it when you see it again. Well, if I hand it over to you, very likely what you're going to do is to look at this object from different perspectives, different directions, and then that set of images you're going to somehow convert into a representation and tuck it away in your brain. You don't know exactly what that representation is, but it's some compact representation. And then when you see this object again in the future, you're able to recognize it. So we're going to take a similar approach here in the context of appearance matching for computer vision. So let's say you're given this object right here. And in this particular application, let us say that we expect the object to be in this stable configuration that you're seeing right here. We talked about stable configurations in the context of binary images, if you remember. So it sits in this stable configuration. And so then we say that there is one pose parameter that is of interest to us, which is the rotation of the object in the stable configuration. So let's say that that parameter is omega-1. So we can place it on a turntable and simply spin it around and capture a set of images. It may be possible that in this particular application, also of interest to you is the illumination of the object itself. And so then you might change the lighting using this robot end effector. You see there's a light bulb there. You could change the lighting direction. And for each one of those lighting directions, you can spin the object on the turntable. And therefore, you get a collection of images where the object is seen under different poses and illuminations. So this is just a simple example. We're going to assume for our purposes here that during learning and during recognition, all the images that we capture can be easily segmented in the sense that the object of interest can be segmented out in full from the image. There's going to be no inclusion and no issues with segmentation. That's an assumption we're going to make to simplify things here. So then what we do is we take all our learning images, segment the object out, and then we're going to scale the object in terms of size so that it fits into some kind of canonical size, shape. And so that's what you're seeing here. These are the image sets that have been captured for four different objects. We're only showing here the images under a single rotation of the object. Now you may have similar sets for different lighting conditions as well. Okay, so that's in what's referred to as an object image set. So now, how do we perform recognition? Well, the most naive way of doing this is to simply perform template matching. You're given an input image, and then you assume that you can apply segmentation to the image. You can extract the object out, rescale it into that same canonical size that we talked about, and then you simply apply template matching, image for image. And you compare this image with all the images in your database, perhaps different objects, different external parameters, and you find the closest match. And template matching, of course, can be done using sum of absolute difference, sum of squared difference, or normalized correlation to handle things like brightness changes and changes in camera gain and so on. But irrespective, you can very quickly see that this is not a practical approach given the number of images that we are dealing with here. So template matching, perhaps in a typical recognition system, a fairly modest one, may have to be done with thousands of templates for maybe millions of objects. Just way too expensive and too time-consuming for any practical application. But there is hope. So if you look at this object image set of a single object right here, and if you look at consecutive images, you see there's enormous amount of correlation or similarity between these images. In other words, this image set that we're talking about is highly redundant, and we can exploit this redundancy. And the way we exploit this redundancy is by taking this image set which resides in high dimensional space, because this dimensionality is the size of the image, the number of pixels. That's a high dimensional space. We're going to exploit this redundancy to reduce the dimensionality of the image set. So we exploit the redundancy to achieve a compact appearance representation in a reduced dimensionality space. That's what makes appearance matching efficient. So one of the key goals here is to come up with a way to perform this dimensionality reduction.